There was a time when a mechanic didn't do much besides change the oil and rotate the tires. But today, camera calibration is actually one of the critical tasks that a mechanic may find himself doing. Here we see an example from A1 glass. When you replace your windshield, your ADS camera systems need to be recalibrated. Much of calibration is in the realm of computer vision. Here, our focus is on the physical imaging systems. But computational imaging relies critically on accurate forward models, and these require calibration. We discuss examples of calibration in the next two episodes. Computational imaging. Episode 60, Intrinsic Calibration. Camera systems need to be calibrated to understand the forward model of the imaging systems. Intrinsic calibration consists of measuring the internal parameters of a camera, such as its focal length, its principal point, meaning where's the center of the image, and then lens distortion coefficients, and things like barrel and pincushion distortion. Then we have extrinsic calibration, which we'll talk about in the next episode, which relates the camera to the external world. Intrinsic calibration is typically measured in a test lab. Here's a lab recommended by Imatest, which builds image testing software to do intrinsic calibration of cameras. And usually you control the lighting, you control the target and the camera position, and try to measure these internal parameters of the camera. You need to know something typically if you have an integrated camera system. There's an ambiguity between the focal length of a camera and the pixel size that's difficult to resolve from just images itself. So typically you know what sensor is used, and you know the pixel pitch of the sensor. If you don't know that, you can do like what's shown here, break the camera open and measure the focal plane, and then you can get the pixel pitch certainly with a microscope, but also through diffraction, because the pixel array is typically very uniform, and so if you illuminate it with a laser, you'll see a diffraction pattern, and the angle of that, the principal frequencies of that diffraction pattern will tell you what the pixel pitch of the camera is. But typically we start with a specification like what's shown here for a Samsung S20 camera. It has 3 cameras, 2 12 megapixel cameras and 108 megapixel camera. Here you see the focal lengths are unreasonably long, like the telephoto lens is spec'd at 120 millimeters, which would be 6 inches, which is of course much thicker than the cell phone itself, and even more than the length of the cell phone. So you might wonder how a cell phone could have a 120 millimeter focal length lens. Focal lengths quoted for consumer electronics are often 35 millimeter equivalent focal lengths. This means that if one imagined that one had a sensor that was a 35 millimeter sensor, what focal length would give the same field of view as the much smaller focal length and the much smaller sensor gives in the consumer device? The conversion factors of this depend on the sensor geometry. Here we see various sensor formats, 4/3 and 2/3 sensors, and whether you measure the 35 millimeter size along the diagonal or the width. But basically you would take the 35 millimeter sensor size divided by the dimension of the actual sensor that you're using, multiply the actual physical focal length by that factor, and you get the 35 millimeter equivalent focal length. For the Samsung Note 20, the actual focal lengths are 2.27 and 14 millimeters. The 14 millimeter sensor is a 4/3 sensor, and then the 35 millimeter equivalent focal length, we multiply the actual focal length by nearly a factor of 10 to get this 120 millimeter equivalent focal length. So that's not the issue for today, though. We really want to talk about how to characterize the intrinsic parameters in the lens performance. If we happen to know the sensor size, we could measure the focal length by measuring the magnification. So once you know what a pixel size is, you can look at a real object size in real space and measure its magnification in the reconstructed image and calculate the effective focal length. Here we see images of the same scene from the 3 different sensors on the Samsung, and you see the difference in the field of view based on the focal length. In the GitHub site, along with this course, there is a GitHub notebook there's a Jupyter notebook that goes through a slanted edge MTF measurement for characterization of the modulation transfer function of lenses for a given camera. When you do this, you would like to work with raw images because then you're not dealing with any sharpening or processing. You're just trying to measure the actual physical performance of the lens. Samsung allows you to capture raw images, which is interesting, of course, when you have 100 and 200 megapixel images, because it's not really the raw sensor data in that case. There's necessarily some processing. So increasingly, sensors that are oversampling with very large pixel counts what they deliver as a raw image is already been processed in some way. But where we have these 12 megapixel sensors, you can capture the raw bare data. And so here's an example from the telephoto lens on the Samsung S20. Here you can see the color modulation from the bare pattern in the pixels. We can separate the color planes, as we saw way back when we were working on demosaicing. And so here at the top, we have the two green channels, and on the bottom left is the red channel. The bottom right is the blue channel separated out of the raw data from this image. So we'd like to calibrate the intrinsic parameters of this system from measurement data. The most fundamental parameter is the frequency response. What is the real MTF of the system? We're assuming that the system is a shift invariant linear imaging system, of course. S of x is here the system response. And we can put a known input in and try to measure S of x. So normally we're trying to estimate f of x from g, but here we're going to know f of x, and we want to estimate s of x, the system response. So for example, we could say that f of x is an edge, that for x less than 0, x is equal to 1, and for x greater than 0, x is equal to 0. So then g is the integral from minus infinity to 0, since that's the range over which f of x equals to 1. If we shift our variables to put this x in the integrand, we get this form for g of x, the measurement that we would get. So normally you would expect g to be 1 from minus infinity to infinity, and then go to 0 for x greater than 0. That doesn't happen because the impulse response can't respond that fast. If we take the derivative of this measurement that we get as g of x, we have an estimate for s of x, the impulse response along the x direction if it's a two-dimensional image. This idea of using an edge to characterize the MTF is the subject of an international standard, ISO 1233, that's described in the paper referenced here. The basic strategy is to shown here. Number one, we find an edge in an image, or we create an edge actually, and then we find points and rows across the edge, as shown in B. That if we plot in each one of the rows, we see the edge, but the edge occurs at a different point laterally because of the slant. But we can shift the points to align them along the edge. This allows us to get some super resolution because we can get subpixel shifts in the relative arrangement of the points, and this is where an edge is better. Of course, we could try just to measure the impulse response by measuring the response to an impulse, but in that case we would be pixel limited. That it would be difficult for us to see effects on a finer scale than the pixel itself. But here, by aligning the shifted points along the edge, we can get effectively subpixel shifts in the response and resolve the response even beyond the pixel level. We then try to smooth the pixels, the measurements, is for reasons that I'll show you in just a second. And then we can take the derivative of the edge function, and basically that gives us s of x, the impulse response. And then if we take the Fourier transform of that derivative, we get the MTF. There's a MATLAB code freely distributed for this standard at the website shown here, this Burns Digital Image. You go there, you can download a MATLAB script that will take an edge in an image, and then of course there's lots of commercial software that will also calculate these kind of functions. Here we're interested in learning more about how this really works and what happens with real image data, so we're going to use a Python code that's in the Jupyter Notebook. Here's an example of an edge from a resolution chart from the telephoto lens of the Samsung S20, and here you see the edge in the red-green and blue channels with the two greens at the top. The pixel pitch on this sensor is 1 micron, and so when we go to each one of these color channels, we're sampling on a 2 micron pitch because we've separated the color channels out. There are many ways we could think about how could we account for color in this system. What we're going to do in today's episode is just take one of the color channels and find the impulse response for that color channel. So now we can take the green channel, and if we take the derivative along the columns, this is just using NumPy's derivative function, we see the derivative along this edge, and then this line is something we can analyze to get the slope of the edge. What we do, in fact, is take the minimum value of the derivative, since the derivative is going negative here, and then that tells us gives us an estimate where along each point the edge crosses. We find the slope of that line. Here's the slope for each one of the color channels, and that tells us the slope of the edge. Here we're just plotting along several of the columns the signal value as a function of pixel position, and you see that because the edge is slanted, the position of the transition of the edge is shifting to the right as we go along. But now we can go and shift these pixel transitions with the amount proportional to the slope of the line. And now this is all of the points, all the signal values measured across that edge, shifted to by their relative position according to the slope of the line. And now we get a relatively dense plot through the transition, where if we look on any one of the edges, we would only have 1 or 2 pixels across the transition, but now we have lots of pixels across the transition. Now we get to the hard part, because you see in real images, especially where the signal value is non-zero, you see a lot of noise. And the reason that there's more noise where the signal value is non-zero is because it's Poisson noise. Where the signal is 0, there's no Poisson noise, and where the signal is high, we see more fluctuations from the Poisson noise of the signal. So how do we find a smooth plot through here and plot the derivative? There's ways that's done in the standard, and I encourage you to read some of the papers on the standard to figure that out. What I've done in this notebook is to use a fit the data with an ERF function. So assuming a Gaussian impulse response, we fit with the ERF and plot through there. And then if we take the fitted data, you see that we get a smooth transition as shown here, and then we can use the parameter of the exponential through the ERF to get the MTF. And so the ERF function is just assuming we have a Gaussian impulse response across an edge, we would integrate that response. The derivative is the Gaussian. Of course, the Fourier transform of a Gaussian is still a Gaussian. So for this particular example, when we take the fitted data, this is what the line shape function looks like. So this is a cross section of the MTF. We get the horizontal data in microns because our native sampling is in pixels, but in this case we know that the pixel pitch of the sensor is 1 micron, but the pixel pitch of the sampling is 2 microns because we're only looking at one of the color channels, which is sampling every other pixel. Then we take the Fourier transform of this, which in the case of the ERF just means plotting with the known exponential, the variance function we got for the exponential, and we get this. And so Nyquist for this 2 micron sampling pitch would be the 500 line pairs per millimeter. We're not getting any significant response up to Nyquist, but we are getting some response up to several hundred line pairs per millimeter. But you do see that generally speaking, these systems are potentially a little bit oversampled compared to what would happen at Nyquist. In the GitHub slides, there's several other examples, or a couple other examples of images. When you do this, you can, of course, get nice commercial resolution charts and a nice setup like was shown with the IMATEST data. But you can also do this on your own. So here's some resolution charts that were just printed out and taped to the wall. And here I'm testing a Galaxy A6 tablet camera from about 2 meters away. You can look both at edges, and then a lot of times you can also look at resolution features in the target to see what's happening to different kinds of features. And these ideas of periodic features are popular because then you can kind of directly measure MTF by looking at the response to a periodic signal. Newer cameras may or may not allow you to sample raw data. In Android, there are many applications you can use to capture raw data if your native camera does not capture raw data. Here I've used this Open Camera app to go and capture raw data here from a Samsung S23, which has a 200 megapixel primary sensor. So you don't get raw data from that, you get some kind of process data. In capturing with the Open Camera app, it's capturing from the ultra-wide sensor, which is 12 megapixels with a f2 lens, and then I also captured with the Samsung Tab A6. This one has 1.12 micron pixels, whereas the Samsung S23 has 1.4 micron pixels. The focal lengths are also different. You can't really tell from the frequency response on an image what the quality of the camera is independent of the focal length. But here's a look at these, the resolution charts, or these frequency charts to see how the different cameras are responding. You see that the S23 does a substantially better job than the tablet. As you look through these charts, of course, the charts themselves have contrast of 1. They're going from 1 to 0. As you plot, like for example with the S23, when you're plotting the low frequencies, you can see a very high modulation, and here the curves are shifted vertically to allow you to see the different curves. But the blue curve at the bottom is a plot through the low frequencies at the right of the image, and then as you go up, we're shifting over to the left of the image, and then we're shifting to the right and going to higher and higher frequency parts, and you can see that the range of modulation is decreasing as we go to higher and higher frequencies. And at the right, you start to see also some aliasing at the high frequencies. If we compare this with the tablet, as you go to the high frequencies, basically the frequency modulation is lost and the signal becomes constant. So you can compare response just by looking at what happens with resolution charts. We go to the edge. There was the center of the image. You can see this is on the left the edge plot from the S23, and on the right from the tablet. Again, we can take the derivative horizontally and get the line that corresponds to the edge and find its slope. One thing you'll see is that the A6 is a lot noisier than the S23. You could try to increase the illumination to try to reduce some of that noise, but the reason for the increased noise is that the pixels are so much smaller, so you get a lot more fewer photons and a lot more shot noise. Here's the aligned pixel plot after you found the slope for the S23 and then fit it with an ERF function. For the A6, the signal is just extremely noisy, as you see, and so the fit did not work well in the example that's given in the notebook. You could try to get more signal to try to reduce the noise, but it can be very challenging to go in here and get a good fit when you have such high levels of noise. Here's a comparison of the measured MTF for the S23 wide field imager and the telephoto. The telephoto, of course, has higher apparent angular resolution because it's got a narrow field of view, and you zoom in. But of course, the angular resolution of an imaging system is not directly related to the MTF. This is image space MTF, and it's telling us the F number, basically, what is lambda F for this system after we've accounted for the distortion of the lens. So even though the wide field is a shorter focal length lens, it has much sharper images on the sensor than the telephoto, which is typical because as you make a longer focal length lens and fold it into a camera, you're going to get a larger F number, which is, in the case of the telephoto here, it's quoted at f3, whereas the wide field is an f2 lens. So this is not meant to be a definitive exploration of testing and evaluation of these cameras, but it's meant to introduce you to the methods and thinking that goes behind this kind of evaluation. And of course, as was shown in the beginning with the Imatest components, intrinsic testing can get much more sophisticated than what we've shown so far. But we need to move on, and we're going to talk about extrinsic calibration next. Here's two images shot in the desert in Tucson, looking out the window at cactus. These two images are from slightly different perspectives, and we need to figure out how to align them, which is what we'll do in our next episode.